Good afternoon, everybody.
Good
My
afternoon.
name is Tar. Hello.
Good afternoon.
Okay. I would like to thank iCoditech for the opportunity to share my work on their platform on the combined effect of magnetic fluid with couple stress, variable viscosity, and velocity slip on the lubrication of finite journal bearing. I'm a maths instructor in the prior learning foundation prior learning at the University of Trinidad and Tobago. Also, I'm a PhD student in the Department of Mathematics and Statistics in the University of the West Indies, St. Augustine, under the supervision of Dr. Rao and Dr. Commission. My topic, it falls under the broad heading of tribology, which is the science of lubrication, wear, and friction. It comes from the Greek word tribos, which means rubbing. It deals with where is the gradual removal of material from one surface, and a lubricant could be any solid, semi-solid like grease or liquid or gas that is placed between two moving surfaces in order to reduce friction. Friction, which is the opposition to movement. So lubrication is where we place a lubricant between the moving surface in order to reduce friction. So under tribology and the journal bearing, so we have the journal bearing consists of a bearing, this non-moving part, and our journal. The journal here is the center of the bearing and the center of the journal. The distance between the center of the bearing and center of the journal is called eccentricity, written as E. And this C, which is the clearance, is the radius of the bearing minus the radius of the journal. The fluid film between the moving parts is characterized by the formula H of theta, where theta is the angle measured. So here we have this line drawn through the center of the bearing, center of the journal, and a line from the center of the bearing. The angle formed between that is called theta, which is the circumferential coordinate. Whenever we divide the eccentricity by the clearance, we get something called eccentricity ratio. At this point here, we have maximum film thickness of the fluid, and here we have minimum film thickness. Also, we have a displaced wire, okay, at a distance r0 from the center of the bearing. When we take that distance divided by the radius of the bearing, we have something called the distance ratio. Sorry. Okay, and this angle here formed, according to Tarapu, the maximum angle, the optimum angle to place this wire is at 90 degrees. This current carrying wire will be responsible for the magnetic field. Here we have our magnetic fluid, which is the fluid consists of three parts. A base fluid, which is we use as couple stress fluid, a magnetic particle, and also the surfactant. The surfactant head is attached to the body or to the magnetic particle, and tail is an elastic cushion which keeps the magnetic particle apart so that they would not come together or aggregate together due to the van der Waals forces. The diameter of the magnetic particle is about 10 nanometers and the surfactant tail is about 2 nanometers. The objective is to study the combined effect of the magnetic fluid, couple stress, velocity slip, and variable viscosity on the pressure distribution, load carrying capacity, frictional coefficient in the lubrication of the finite journal bearing. The governing equation, where rho here is your density, U is the speed, and P is your pressure, and here this is the external force, your body couples, and mu will represent the kinematic viscosity, and eta is the parameter that is responsible for the couple stress. Under some limiting assumptions, this would reduce to the form here, and to get this together with these boundary conditions, we solve for U, and we will solve for U. Here in U, when we find U, the velocity in the x direction, we have here alpha, which represents your piezo-viscosity parameter, lambda, your slip velocity, and L will be a couple stress, all incorporated to solve. We place this value into the continuity equation and we come up with the modified Reynolds equation. And from this modified Reynolds equation, we solve. And when we solve it using finite difference, we will place that into we'll integrate that pressure over the area to find the load carrying capacity. The force will be given by this formula here, and we'll use the force over the load carrying capacity to get the the frictional parameter. The result shows that here we have the pressure versus the circumferential coordinate. All right, we have L, which represents the couple stress. So in the absence of couple stress, we see that there's one peak maximum pressure, which is due mainly to the magnetic parameter. And we see that there's an increase in the magnetic parameter here as we increase our piezo-viscosity parameter alpha. Here the distance ratio is 1.2 and the eccentricity ratio is 0.6 and the magnetic parameter we are using is 2.0. Now when we introduce the couple stress parameter from non-zero, we see that there is two maximum peaks that are occurring, or two peaks, and one due to the magnetic parameter and one due to the hydrodynamic parameter. And as alpha increases, we see that the peak increases, so that the piezo-viscosity parameter does affect the maximum peak value. Also, when L increases the greater, we see that the hydrodynamic pressure is greater than the magnetic parameter. So high pressure occurs with high values of couple stress parameter and high value of piezo-viscosity parameter alpha. Also, we have a numerical value showing as alpha increases from 0 to 0.35, the maximum magnetic pressure increases both for the maximum magnetic and also the maximum hydrodynamic pressure. So the lowest occur at 0 when there's no, because this piezo-viscosity parameter is concerned with the variable viscosity. And as we increase that, we see that the maximum pressure occurs, increases for both magnetic and hydrodynamic pressure. Also, how does it affect the load carrying capacity? So load versus couple stress, as the couple stress increases, the load carrying capacity increases. We see also when the piezo-viscosity parameter increases, so does the load carrying capacity. In each case, when alpha 1 is 0, that means in the absence of the magnetic parameter, the load carrying capacity is less than in the presence of the magnetic parameter. Okay, so also we have when we have load versus slip, you see when we have a high slip, when slip is we have the highest load carrying capacity of the bearing. And as slip begins to increase, going to the no slip condition, you see that it causes a decrease in the load carrying capacity. But of course, we have when we increase alpha, when alpha goes from when alpha 1, which is our magnetic parameter, from 0 to 2, you see that every time we add in the magnetic parameter, the load carrying capacity is increased, and also it is increased with the increase of the couple stress parameter. And so we have here with load versus the distance ratio, that is the distance it is from the bearing. From around 1.2, we see that the load would increase when we increase the magnetic parameter. But as we increase and we go further and further away, if we put that current wire further away from the bearing, you see that the effect becomes less and less and the load carrying capacity decreases. Here we have friction versus the distance ratio. So we see we have a 1.2 when alpha is 2, we have a high, alpha 1 is 2, we have a high friction parameter, but when we increase alpha 1 to 8, it reduces. After 1.2, we see that the reverse effect is happening. Here also for the frictional parameter versus couple stress. As couple stress increases, we see the friction decreases. All right, and between 0.45, less than 0.45, when alpha 1, which is the magnetic parameter, increases, so it decreases the frictional parameter, and after 0.45, the reverse trend occurs. So the frictional parameter versus the slip, so as slip increases, we see that there is an increase in the friction. So large slip implies a no slip condition. So in conclusion, I just want to say that the maximum magnetic and hydrodynamic pressure increases with increasing piezo-viscosity parameter in the presence of the slip parameter. Higher load values occur in the presence of the magnetic parameter, high eccentricity ratio, and higher piezo-viscosity parameter. For an increase in the magnetic parameter, the friction decreases. The combined effect of high couple stress parameter, low piezo-viscosity parameter yield the lowest friction. From the above results, we could enhance the journal bearing parameters characteristic by combining slip, piezo-viscosity, and couple stress according to our application. One application here is that this could involved in the reduction of startup friction. The magnetic particle have the ability to be retained at some desired position. So the metal-to-metal contact will be avoided without the need of any external lubrication. These are some of my references, and thank you.
Okay, thank you, Mr. Tyrone, for the presentation. So we are expecting questions from participants.
Okay, our first question is from Dr. Betru. Since temperatures are likely to increase with high velocities, would your model be able to incorporate this?
Right, this is a good question because I didn't consider any temperature, but I think in some future work I was deciding that maybe I should put in temperature and see how it will affect the whole model, because that will be an extra term and it will be good to see how much the temperature will affect the whole setup for the journal bearing and its optimum use.
And there's a follow-up question. Is the model applicable for extreme positions of the journal bearing?
When you say extreme position, what are you talking about exactly?
The different angles, the ultimate angle that the journal can go to the axis.
Well, the angle that we use is from 0 to 180 degrees. All right. After that, what will happen is that we'll go to the cavitation region where the pressure is inverse. So I think it will be able, depending on how we increase, for example, that couple stress parameter, if we keep increasing it up, well, the level we go is up to 1. All right, so 0.9. That may be able to capture some of those extreme areas to avoid any of the frictional problem that may occur.
And large eccentricities.
Right, large eccentricity also affects the maximum pressure, but we didn't get time to put in all of those graphs because, you know, the slides were limited. But I did consider where the eccentricity ratio was increased, and by increasing the eccentricity ratio, we have the maximum pressure increasing very good, because if we want to have a large load carrying capacity, we could do that. But remember, not every situation will want it to be carrying a large load, might be a small load, depending on its application.
Okay, thank you.
Okay.
I have one question if I have time. No time? Shucks.
No,
Okay.
Still one time, 1 minute.
1 minute?
Yeah.
Okay. You had two graphs, I think it was the Turtlead slide, where both sets of graphs, you had 4 graphs on each, and the both sets intersected at particular points. What were the significance of those points of intersection?
Right, that was interesting because I was very glad for that. You see, because it depends on the value of one when that couple stress parameter begins to increase. All right, when it begins to increase, it seems like because of the characteristics of the couple stress, it adds up, like you see, is more because the couple stress deals with long chain molecule, and the greater it becomes, is the more enhanced it becomes to avoid the to even increase like viscosity and thus reducing the friction. So the more the greater is that couple stress parameter, is the more it will cause the friction to be reduced. So we see that when it is less, we see what happening is that the value it
Time
changes.
up, please.
So, and also when we have remember what the distance ratio.
We like to thank you.
Time up.
Okay, all right. Okay.
Thank you very much.